We are recording.
Cool. Let's just make sure that is off and not distracting. Yeah, so we're going to go over technical decision making. Basically sort of why, how, and when you want to be able to do it in a project or whatever you're working on to make it useful and ideally make the project successful. So the first thing is really the why. Since that's really important for basically anything, you want to know why you should do it. This chart is a bit of an example of going through a typical project. And while this isn't going to be the same for everything, it's very consistently similar to this. And you can see that basically as you go through concept development and designing for your project, your spending is typically low around that point, and then by the time you get to the end of your project, you've spent obviously all of your money. However, it's in those early stages that you're committing those costs towards the rest of the project. So you see that they're basically opposite sort of curves in how they respond. And so as you're working on a project, most of your money, while it's not spent in your design phase, in your initial concept phases, it's allocated for different things that early on. And so if you're making a mistake early on in your concept and design and you have to go back, that ends up just increasing the cost of the project or increases the time, all those different things, and makes it so that you really can struggle with your project. And so your goal is to make the right decisions early on to avoid those unforeseen costs and complications later on. Here I have another diagram. So this one is sort of why you want to be able to successfully pick a good decision. So like I said before, obviously, if you pick a decision early on that you don't like, it's going to cost more later when you have to redo it. And so you want to be able to find, ideally in this green area, where you know that the cost is low, but you have a really good benefit from the decision that you've made. And then obviously you don't want to be in the opposite side of that, where you're making something that's going to cost a lot and do very little for you. And so going through the technical decision-making process really will help you be able to more consistently hit this bottom right corner. You won't always get it because that's just the nature of some problems and the solutions you can come up with them. But ideally, you try to hit that mark as early as you can, and technical decision-making is a good way of being able to hit that as early as possible. There are basically two types of decisions that you really have, programmed decisions and non-programmed decisions. Programmed are those problems that you almost already know the answer to, and non-programmed are the more abstract. You really have to think about some of the more nuanced aspects of your project and of the actual decision-making to be able to make those. As you can see sort of on the sides, really, obviously, programmed decisions are more likely going to be made by people who have less experience or who are newer to the projects, whereas the non-programmed decisions are really going to be the higher level people within the project. There are a few different decision-making conditions, two on this slide and then two on the next. First is certainty. So these really fit into that programmed decision. Risk is a little bit still in that programmed decision, but it's sort of getting close to that line that we saw on that chart. But certainty, you know all the requirements that relate to the decision. You know every single option and every possible outcome for the decisions. And you basically have every single bit of information that you need to be able to make that decision. So like I said, that's programmed decision. you basically know, if I do this, this is exactly what's going to happen, and I know that's the best. That's always a good decision to have to make, because they're pretty easy to make. Risky decisions are similar. You have a lot of those decisions for your requirements well known, and you understand the options and the outcomes, but you don't necessarily know every aspect of them. And that's because some of the information that you have while trying to make the decision is unknown, but you really do still have a large knowledge of the decision that you're trying to make. The next part that we have is uncertainty and ambiguity. And so uncertain decision-making conditions, again, you understand the requirements that you're going to need to meet for your decision. Some of your options are understood, your outcomes really are not understood, and you're missing quite a bit of information when it comes to making the decision. And then an ambiguous condition is you really do not know any of the requirements for the decision. Options for making them are lacking or hard to find, and you have next to no information for making the decision. Now, obviously, those are difficult conditions to work in, and on the other slide, those certain and sort of risky conditions are always more ideal. And so your goal as a decision maker is trying to reach the point where you're in that area. You don't want to, if at possible cost, try to make an uncertain or ambiguous decision. You're really trying to make one in that certain, potentially risky area, so that you can really make sure that you know what you're doing and know what's going to happen once you've done it. However, there is some balancing that will need to be done, and we'll talk about that a little bit as well. But we're going to go over some considerations when making your decisions. So first, and probably one of the most important, is assessing risk within your technical decisions. So you really need to know how likely something's to fail. Obviously, failure of your system or your project is the worst thing that could happen, or one of the worst things that could happen when it comes to a project. And so avoiding failure is ideal. However, you really need to look at how likely something is to fail to really decide how important that decision is. And so, for example here, you don't need to waste your time and energy to analyze every single bolt. You know, in some cases, yes, this is going to be a strong enough bolt. I don't need to do the math for it. And that kind of goes into the next one. You can make assumptions and approximations where possible, but you want to make sure that you understand where they no longer work. So obviously in like fluids and thermal stuff, you can treat water as an incompressible fluid, obviously up until a point, and then you may need to change some of those assumptions. But being able to know, yes, 9 times out of 10, I can do this, and this is good enough, that obviously helps in your decision making, because it simplifies things a little bit. You want to make sure that you're really assessing critical components and critical design pieces to your system. You also want to look at sort of those one-way doors in your project, and think about what sort of solutions you can fall back on, or if something were to go wrong, what other solution is something that you know will work. That's sort of an important thing. Sometimes you may be going into a project saying, yeah, I know that this is the way that this would work, but I think it would be really cool if we could get this kind of solution to work, because it would do X, Y, and Z to improve the project. But if you're going through your project and you see, oh, that's not working the way that I thought it would, you want to be able to have that backup and be able to work on it that way. And now the other thing that I added and it's not really something quite as important with technical decision making, but it's something to keep in mind when you're looking at risk in general, is a factor of safety. So everything really can have a factor of safety and probably should, depending on what you're working on. But basically it's, you look at, this is the failure point, this is the cap. Say, like, if I apply 10 newtons of force to something, it will break. I know that it's going to work in a 10 Newton situation, so I'm not going to build it to survive 10 newtons. I'm going to build it to survive, say, maybe 15. So that way it will actually survive the worst case scenario that you can provide it. And like I said, well, that's not necessarily a technical decision kind of thing. It's something that you need to keep in mind when you're looking at risk in general. The next one that we want to talk about is, what sort of assumptions are you making about this decision? So like I said, you can talk about assumptions, and assumptions are great at being able to simplify problems, especially really complex problems. But you really need to make sure that the assumptions that you're using make sense. So for example, like, you can say, yeah, I know that I can use this assumption to simplify my problem in this way, but that doesn't necessarily make it easier. And so you want to make sure that you effectively simplify the system. Another question worth asking while making assumptions is, if I change my assumption, how might that change the decision-making process? And that's certainly an important aspect as well. One thing that I know that we've been doing with the Break the Ice Challenge team, one of the assumptions that we've been debating on is the state of the water that we will have. So once we've mined water off of the, or from within the lunar surface, and we have it within our robot, and we send it to its extraction site, we then have to take the water and transport it somewhere else. And so the assumption is that the water that we receive is liquid. It could be gas, it could be solid still. That's a really important sort of assumption in that case, because if it's liquid, you need to make sure that it can fit within a sealed liquid container. If it's gas, it's going to be harder to seal within that container. And if it's solid, you don't need something quite as sealed to be able to keep it in. And so being able to know how your assumptions fit with your project can really help in making sure that you pick the right decision. And then sort of in line with that, you have these what if scenarios when you can change those assumptions, and they can give deeper insight even into the solutions that you wouldn't have necessarily thought of fitting those scenarios, but some other scenario that you've already considered. Next is sort of, what environment is the system in? Like I said, working on projects that are in space, or working on projects that are underwater, or maybe in extreme cold or extreme heat, isn't exactly something that you necessarily see in your day-to-day life, some of those conditions that you may deal with. And so just because a solution may work well where you are does not mean it will work well where you need it to. And so ideally you try to perform these tests within the environment, or a similar type of environment to what the system will perform in, and sort of use those tests as a basis for the decisions that you make. And then avoid limiting your potential solutions as well to just the ones that are feasible in the environment that you're used to. So we know that something may work on Earth in like a standard environment, and we know something may not work in that same environment, but maybe it'll work somewhere else. Like maybe with the ROV team, I know that there are some things that won't work above land because they're very difficult to do with the gravity that we have, but they'll work well underwater because you have that additional buoyant force. And so you want to be able to factor those kinds of things in when you're thinking about your design decisions. Next, how good does the decision need to be? Obviously, you're limited on time and other resources that you may have to be able to make these decisions. Like I said, it's important to make these decisions as early on as possible, but you can get into what some people call this analysis paralysis. Nice sort of rhyming term there, but essentially it's you're stuck on trying to make a decision because you're afraid, or you're too afraid that making the wrong one will end up being a big issue further on. And so you focus so much on it that you never get to finish the project. And so you want to make sure that you keep that in mind as you're working on your decision making. You know that you're limited on how long you can spend making a decision. And so you want to avoid focusing on one decision for too long. A good way to think about it is really to focus on those system requirements and maybe your subsystem requirements, and really decide what is the most critical so that you can figure out where you really need to focus your decision making. Again, like we said, do you need to evaluate the strength on every single bolt? Probably not. So you really don't need to spend every minute of every day trying to analyze every single bolt, because you know that it will survive the situations you're putting it under. Now, there are situations where, like, you probably do need to look at the strength of the bolt, and it's important to do it in that situation. And it's really a balance that you need to find to be able to decide, is it really important in this situation? One last thing that I put here is another fairly important one, and I put buying off the shelf. It's not necessarily always buying off the shelf, but buying off the shelf versus making it yourself. So obviously, we're all fairly talented people, and I'm sure that if we tried to put ourselves up to the task, we could make everything that we need to from scratch. That doesn't necessarily mean we should. There are people who do things that are good for a reason. Like there's software that exists for being able to model robots. Why would we need to spend the time and the effort to design it ourselves? Or we know that people make bolts. Why do we want to spend time trying to make our own fasteners? It's just not necessarily worth the time. And so you want to be able to really balance that out and try to figure that out. I just saw a chat come in. Oh, yes, thanks, Ethan. I would say it's a relevant slide because it really is. This is one of the things that I've noticed people like to fall into. You know that you can make something and you can make it better than maybe some of the things that you'll find on like a commercial off-the-shelf thing, that COTS acronym that's there. But I mean, yeah, like there are certainly things that we know that we could probably make better than you may be able to buy. Maybe not necessarily us, but when it comes to people who are designing these systems, though we may be able to make some things better. But there is a balance, and there's certainly the amount of time that needs to go into this. That this is probably one of the most important decisions that you may make while working on a project. Now we're going to go into sort of those steps to decision making. So I guess before I start that, if anyone has any questions about what we've gone through so far. Also, if anyone has any questions at all as I'm going through, please just ask. I know that Ethan was putting some stuff into the a chat here, and I appreciate that. And as long as I see it, I will continue to go through and try to answer anything that pops up there. But if anyone's got questions on anything at all at any point, please just kind of butt in and ask a question. But like I said, steps to decision making. So basically, this is sort of that process that you'll go through. This is, again, really in sort of your concept and design phases. Chart basically will go through it, but I'll sort of go through each point as we continue on in the slides. So I'll just briefly go over this one on some of the next slides. So first off is deciding what the problem is. This one's always sort of an important one because while you may think you know what you're trying to solve, really having that problem statement nailed down prevents you from working on the wrong thing. So again, an example here, mining robot, you have to collect the soil and subsoil underground. In some cases, you may not care to collect that soil. Like if you're trying to only collect, say, a specific mineral, then it doesn't matter if you've collected a ton of the topsoil. If you have none of that mineral, then it doesn't matter to you. And so you want to make sure that whatever problem it is you're trying to solve, you really have that problem statement nailed down. Good way to try to look at that is going through your requirements, which we will have a requirements lecture at some point, along with some other things within that lecture. But as long as you look at the requirements that you've made, it will really help you in sort of nailing down that problem. And then while you're thinking about your problem, you should not be thinking about your solution. Thinking about the solution while designing the problem can sort of push you into a corner and force you into a solution, whereas finding and defining the problem is meant to be as open-ended as you can possibly make that problem. And so thinking about solutions as you're working on defining the problem can sort of prevent that. So you want to try to focus on just the problem. However, once you've nailed down that problem, you want to then start to look at those potential solutions. So it's a little bit of a balance again between when you go from one to the next, but you really want to, once you have that problem, start looking at potential solutions. So again, we had the problem from the previous slide. We're trying to collect things from underground. And so a potential solution is we'll build a robot that can go and mine those things from underground. There are plenty of different ways to come up with brainstorming different solutions. And so I won't necessarily go through all of those. If people want suggestions for brainstorming, just ask me at whatever point you want. But I mean, I'm sure you guys can at least come up with a couple ways of, or I'm sure you could brainstorm a couple ways to be able to brainstorm something. One thing that I will say is that lateral thinking methods typically work pretty well when solving different problems to what you'd normally do. And one of those is like trying to solve the problem in a radically different way than you normally do. Like I said, obviously knowing sort of what's feasible is important when it comes to making a decision. And so if you choose something that's extremely different than what you'd normally do, you may have a little bit of trouble. But really, when it comes to brainstorming, you don't want to focus on necessarily the feasibility of everything. You really want to just sort of throw everything at the wall, and then as we continue through the process of decision making, you'll start to find the things that stick and the things that work better and better. Once you've gone through a couple of these solutions, you'll start to do research on each of them. There are plenty of ways to find different research, like going and looking at patents, looking at actual research studies, case studies, prior work by other people who have done similar things. And ideally, you're really using these to gather ideas. You're not plagiarizing. That's not the goal of designing a project. But again, as you're looking through and doing this sort of research, you're trying to look for things that can help solve your problem. What's an interesting way to maybe try to look at this is to sometimes even avoid some of the what I'd call traditional research for that sort of problem, and maybe look in a very different way. Like researchers and people who will do stuff for robotics and design robots for many, many years, we're all looking at hard, rigid frames to be able to design their robots. And then some people said, yeah, but if we look at biology, we see there's a lot of soft creatures and a lot of compliance within those things, and they succeed 10 times better than half the robots that exist right now. What if we tried to mimic biology compared to these robots that we currently have? And sort of switching to that has really opened some different areas in robotics. And so sort of looking into different fields and different potential ideas, while that sort of is also with that brainstorming and goes into research, can really help you gain new ideas that you wouldn't necessarily think of if you were just one-track mind on solving your problem and looking at what already exists in that area. Once you've gone through your research, you'll start to do trade studies, and they're basically taking this research, really dividing it up into each of your solutions, and then trying to decide which one is the best for your project or the best decision that you can make. Typically, you're looking at things like cost, risk, efficiency, how close it matches your requirements, and you're really trying to compare those things in a way that gives you the best solution that you can have. Trade studies you'll find are typically used in a lot of the decision making of a project, such as developing system architecture, making those make-buy decisions, or resolving conflicts. This chart is a little bit of a different way of looking at sort of that trade study process. And so you start with sort of the constraints of the project, some of those existing requirements and assumptions that you have, and then you'll go through and you'll sort of determine the scope of your trade study. And as you keep going, you'll start to come up with ideas and criteria for how you want to grade your different solutions. And then you'll eventually end up with some trade study results that include some data, maybe graphical, as well as probably the most important is the recommended solution and potential benefits of that solution compared to others. Now this one may look a little intimidating, and we don't do this one quite as much on the robotics team, but this is an example of something called a trade study tree. And so when you have a really complex project with a lot of different decisions that need to be made, you can make something like this where you help sort of break down those different decisions. So this is an example for a human expedition on Mars that NASA had thought of years ago. But it's basically sort of looking at what are the different sort of decisions that they may want to make, and sort of where in the project those line up, and how when you break those things down, what they will end up actually doing in relation to the rest of the project. And so what's good about something like this is that sort of you can backtrack where every decision comes from and how every decision affects the decisions or the other decisions that exist. We'll start to go now into decision-making methods. And so this is sort of, again, really probably the most important part of this lecture in being able to get an idea of how you're going to make these decisions. So there are a few different ways of trying to make decisions. One of the simplest is just a pros and cons list. You look at the different solutions, you list down, this is what's good about one, this is what's bad about one, this is what's good about the other and bad about the other. You then compare them and say, yeah, this one looks pretty good. Now, sometimes pros and cons lists are good. You'll find that they aren't always going to be good enough. And so we'll go into a little bit more complex methods of coming up with decisions after this. And this is something to keep in mind with all of these decision-making things. But when you already have a solution that you think, this is the one that I want to do, you'll typically be biased. Pros and cons lists, you'll see it more than you will in some of these others. And so you really want to try to avoid that sort of bias. It's much more difficult, at least in my opinion, in these pros and cons lists. It's a little bit easier in some other situations to avoid that. And like I said, we'll get into those, and they'll make a little bit of a better way of avoiding that bias. But you must be aware that that bias will exist in every decision you make. And so you want to try to avoid it as you're going through your decision making. Here we have a couple of different rating methods. So the top one is a pew chart. I will say that this isn't necessarily the same structure that most people keep their pew charts. They normally have it so that the solutions are in columns and then the measurements are in rows. But this is a template that we have in our drive, and so that is how I've presented it here. Pew charts are probably one of the simplest matrix methods of being able to evaluate a decision. You have a solution that you've called your datum, and so your datum is the stock standard solution to that problem. Not every situation will you have a stock standard solution. So you'll pick the one that maybe you want, if you want to say it that way. Though again, you're trying to avoid bias, so calling it what you want isn't necessarily great. But you have this datum that is just constant value. And then you have your other alternative solutions. And with a pew chart, you just ask, okay, is this alternative better or worse than my datum? And that's all you do for a pew chart. And what you'll see with those is they'll start to give you an idea of, again, sort of in the way that you could get pros and cons in comparison sort of to this datum solution that you have. One other thing that I'd like to mention as we look at these is I tried when making these templates to have solutions which were consistently the same in their qualities and the actual alternative solutions. And what you'll notice between these two is different solutions were picked between the two methods. And that's not an uncommon thing in any of these decision-making methods. So that's something to keep in mind as well. But I will sort of go on to this other one. So the weighted rating method sort of takes the pew chart and skews it slightly. So In this case, you're now ranking sort of your qualities and looking at them. So you can have a scale. So like before you had, okay, it's better than my datum or it's worse than my datum. Whereas here you say, okay, it is 2 times better or it is half as good. And so you can sort of have a bit more of a scale. And then you also have this weighting percentage, and that goes towards your qualities. So like I said, say you're looking at efficiency and cost of 2 different solutions. You may say that efficiency and cost are equally important to you. And in that case, you can give them the same weighting. But what if efficiency is more important than cost? Then using this weighted rating, you can scale them proportionally so that way you can find the best solution in that way. Now the third sort of matrix method that I have here is called the Kepner-Trigo. I think that's how you pronounce it. It's very similar to sort of that weighted rating, but you try to include the numerical values that you're trying to pay attention to, and you separate out into your must and wants. So when we talk about requirements, you have requirements that you know you need to have, and then you have some requirements that you would like to have, and trying to get the balance between those. Obviously, you need to make sure that everything that you need to have is there, and everything that you want to have, you try as best as you can to get. And so using a method like this, you're able to essentially look at the things that you know you need to have compared to the things that you want to have. In this situation here, all of them do meet your must-haves, which is good. Ideally, you pick solutions that can make or can actually make a successful project, but maybe you find a solution that beats the other solutions in all of your wants, makes the absolute best thing in all of your wants, but it doesn't hit one of your needs. If it doesn't hit a need, you can't use it. So those are more binary sort of solutions up here. If you end up not hitting it, then you should not pick that solution. And again, this one is an example of one that is actually filled out and is looking at a couple of different options for vehicles. Again, you have sort of the weighting for how important those different wants are. This value is similar to what we had on the weighted rating, where you're sort of grading them, but you're grading them based off of numerical values that you were actually able to collect while doing research for these. Another one, which we don't really do on the robotics team because it takes a good bit of time and resources, but is a pretty useful one if you have the ability to, is called this Delphi technique. Essentially, you give a bunch of different people all of the information and research that you've acquired to be able to try to solve your problem, and you ask them to pick their best and give their reason as to why. And then you look at all of their reasonings and all of their personal opinions, and then you go about making the decision. What's nice about something like this is you can ask people in a wide variety of fields for their personal experience in a solution. And being able to do that really helps you actually get a good understanding in some fields that you may not be great in. Like, I know I'm not really experienced in software or hardware engineering. And so if I'm going to go make a decision that involves programming a robot or designing the hardware for a robot, I'm going to ask someone who knows better than me if the solution that I'm thinking of makes sense. And so that's maybe a smaller scale version of this Delphi technique. But it's a good way to sort of look at it and think of applying it, even if you don't necessarily do it as structured as I'm explaining here. Another one that's important, just group voting. Obviously, if you're working in a team of people, they're going to all have opinions, and trying to sort of vote on a solution will help give the best that fits the most people within the group that has to work on this project. Last thing I think I'm going to give, I think is the last thing that I have on sort of the different methods, is what if you decide that the solution just doesn't feel right? Sometimes you'll make a decision and you're like, I don't know, just sort of looking at these, if that's really the one that makes the most sense. If it doesn't, you should at least take another look. Gut feeling obviously does mean something. And like I said, you're trying to avoid your biases, but sometimes you have a bias for a good reason. And so you want to potentially look at some of those things that you may have glossed over when it came to the method that you were using for making your decision. Obviously, again, looking for biases, sometimes you may think something is higher priority than it really is. Like, I will probably put more priority towards a mechanical component than a software component. And because of that, I may choose a solution that is really difficult on the software side. That's not necessarily good. And so trying to sort of look at some of those biases and decide if it makes sense the way that you have it is important. Also, make sure that it fits your major need sort of requirements. That may be part of the reason why you don't feel like it makes sense. Last is, don't rely just on those numerical data points that you may gain. So like I gave you a bunch of different matrices that give you definitive numbers. This is the best solution. That doesn't mean it is. As we saw, your Pew chart and your weighted rating, I tried to make those two solutions the same. They weren't. You'll find that depending on the method that you use, you will end up having different solutions. And so there is some subjectivity in making your decision and choosing what method to make your decision. Last thing I'm going to go over, and this one should be a little bit quicker. I know we're getting close on time. Is just dealing with decision changes. So quickly, this is commonly known as the good, fast, cheap triangle. You've got 3 points. You've got time, which is sort of that fast part. You've got good, which is down here, your scope, and cheap is your money. You have a limited amount of each of these. And what you'll notice is if you start to lack one, you will need the others. So for example, if you are lacking money, you'll notice that you either have to reduce the scope of the project or increase the amount of time that the project is, or depending on what sort of resources, you have to decrease the amount of time the project is because you've run out of money to pay people. You've got time. So if you're running out of time, you're going to have to, again, either reduce that scope or say, hey, I need a lot more money to get this done in the amount of time that we have. And then again, you have, if you start to increase the scope of your project. So I know the last one of these lectures we had, we spoke about scope creep and sort of that function of you start adding more and more to your project because either out of necessity to make the project successful or because you've started to have some deficiencies in the project management, you start gaining stuff to your scope of your project. It will either then take more time or cost more money, probably both. And so that's sort of what this triangle will do. And when it comes to sort of working on making these decisions, you need to keep that in mind. Again, like I said, big part of making a decision is trying to make sure that you make the best one as early as you possibly can. So that way you can prevent having to change how you're working on the project later, which will either cost a lot of resources, cost a lot of time, or change how the project's success could be. And so really trying to balance those as early as you can sort of help prevent these sort of problems you may hit in that good, fast, cheap triangle. And this is about the end of the presentation, I think. Yeah, looks like the end. If anyone has any questions on any of what we went through, now would be a good time. If not, thank you for listening. And I know that we're going to start the other meeting here pretty soon.
You're in about 10 minutes until GB. Thank you, Robert, for giving this presentation.
Yeah, no problem. I think, oh, no problem, Maranya. But yeah, if there are any questions, just now's good time. If there aren't, I mean,
I have a comment on the Delphi method. I've sort of been doing this for a while without realizing it. And I think it was like high school for robotics. They were like, talk to anybody you know about this and see if they have a good idea. Because
yes,
that works really well. And I have this relationship with my dad, and that's how, I don't know if you guys have been following the random thread about spinning ball of death with buckshot. But that's something he came up with, and I never would have thought of that. And it's not going to work, but it's going to be fun. So bounce things off lots of people.
Yeah, obviously, the more minds that are really deep into a subject can definitely help. And so that Delphi method is a really useful one. And like I said, we don't necessarily do it very strictly on the team, but it's still something that happens. We do ask people who have better experience. We ask former members to join design reviews and give their opinions. We ask Bachman to come in and look at what we do and critique us on it. Ethan asks something though. Does PewChart compare to a solution you've already had in mind, or is it for all unpicked solutions? So that it depends. If you're looking at improving something, so say you already have a process that you're working on, like on the mining robot, we have a bucket conveyor for collecting material. We can call that our datum. We know a lot about that solution, and then we can compare it to other potential solutions and say, okay, this is better, this is worse. However, you won't necessarily always have that because you don't always have a legacy system or legacy experience on a similar system. And so in that case, the datum may be more so something that you have in mind, like the solution you may think you like most, or maybe is the first solution you come up with to the problem. It is a little bit more ambiguous when you get into that situation. Also, just in personal preference, while I did present the PewChart, I personally would prefer using the weighted rating methods, just because, like I said, you can actually look at how each of those qualities that you're trying to focus on do end up actually relating to each other. So, like I said, if you're comparing cost and efficiency, not every time is cost going to be just as important as efficiency. And so you want to make sure that in using a weighted rating, you can actually balance the importance of those different needs or wants. And So I personally will use a weighted rating or another method that sort of is that sort of allows me to actually compare not just the different solutions, but compare how the qualities of those solutions are related to each other. Yeah. Cool. Doesn't look like there's anything else coming through. Yeah, great.